So here's a picture that's sort of what would happen if you didn't try aiming your boat slightly upstream, if you just aimed it directly across the river. So if we did that, then this would be the velocity of the boat with respect to the river. This is how the boat would be traveling if there weren't any current at all. So this is just due to the boat, but it doesn't include how the river pushes on the boat. If there's a current, then the velocity of the river with respect to the earth would be flowing from upstream to downstream, so in this direction. And when we add those two velocities together, we would get the actual velocity of the boat with respect to the earth. So this is the velocity that a person on the shore would measure. So what we want to find in this example is the velocity of the boat with respect to the earth. So we have to make sure that the subscripts match up in our vector addition. So the first is the first, the last is the last, the ones in the middle match. So we should add the boat with respect to the earth plus the river with respect to the earth to get the boat with respect to the earth. So boat with respect to the river, river, earth to get boat with respect to the earth. And in this example, since we have motion in more than one dimension, we need to add these vectors by breaking them into x and y components. Actually, in this particular example, that's very easy because the velocity of the boat with respect to the river is totally in the x direction. River with respect to the earth is totally in the negative y direction. And so we can easily use the Pythagorean theorem to find the velocity of the boat with respect to the earth. This is also a reminder down here that when we switch observers, we also switch sign. So let's look at an example where we have to add velocity vectors in order to switch from one coordinate system to another. So in this example, we have a plane that travels at 300 miles per hour due east, and it enters a region where the wind is blowing 100 miles per hour in a direction that is 30 degrees north of east. What is the new velocity of the aircraft? In other words, what is the velocity of the aircraft with respect to the earth? So we should draw a picture that includes these vectors. So first off, let's draw our axes just to specify direction, north, south, east, and west. And then if I draw a picture of the velocity vectors, the plane is traveling at 300 miles per hour due east. That's how it would be traveling if there wasn't a wind. So here's my coordinate system, and the velocity of the plane with respect to the air, that's equal to 300 miles per hour. And that is due east, and that's how the plane would be flying if there were no wind. However, the wind comes along, and the wind has a velocity that is 100 miles per hour, and it's blowing in a direction that's 30 degrees north of east. So there's my wind vector. My wind vector, this is the velocity of the air with respect to the earth, and it has a magnitude of 100 miles per hour. And it's at an angle that is 30 degrees north of east. And we remember north of east means we start out east and then we drag the vector 30 degrees in the north direction. So if I were to add these two vectors together, the velocity of the plane with respect to the air plus the velocity of the air with respect to the earth, then that would give me the velocity of the plane with respect to the earth, which is the velocity that I am interested in. And that velocity is the sum of these two vectors and would look something like that. So that's how the plane will be traveling if I'm looking at the plane from the surface of the Earth. So I want to find the magnitude and the direction of that velocity vector. So to do that, I need to add together these other two velocities. And the first step, of course, is to break those velocities into their x and y components. So I'm going to start by making a table to break the velocity vectors into components. So first I have the velocity of the plane with respect to the air, and I have the velocity of the air with respect to the Earth, and I need to break these vectors up into their x and their y components. Then when I sum them together, I'm looking for the velocity of the plane with respect to the Earth. All right, so the first vector, the plane with respect to the air, well, that's the easy one, because the velocity of the plane with respect to the air, as I've drawn it here, that's totally in the positive x direction. So I can just write down that that is 300 miles per hour in the positive x direction, and it has no component in the y direction. So then I need to consider this second vector, and I'll draw it again all by itself. That will make it easier to break into components. So I know the velocity of the air with respect to the Earth, the wind velocity, has a magnitude of 100 miles per hour, and I wish to break it up into its x and its y components, and I know this angle is 30 degrees. So then, if I take a look at the cosine of my 30-degree angle, the cosine of 30 degrees is adjacent x over the hypotenuse, which is 100 miles per hour. So the x component is going to be 100 miles per hour times the cosine of 30 degrees. So for that, I'm going to get an amount which is 86.6 miles per hour. So I can put that into my table. This is in the positive x direction. So that would be 86.6 miles per hour. And then if I'm looking at the y component, I need to consider the sine. The sine of 30 degrees is going to be opposite over hypotenuse. So that means my y component will be 100 miles per hour times the sine of 30, and that will give me an amount which is 50 miles per hour. So then I can put that into my table as well, and yes, that's in the positive y direction. It's 50 miles per hour. So then I can add up my x and my y coordinates. So for the x coordinates, or the x components, when I add them together, I will get 387 miles per hour, just rounding a little bit. And then in the y direction, if I sum the components, I get 50 miles per hour. So now I should draw my resultant vector, which is the velocity of the plane with respect to the Earth. So that's going to look like, this. It's going to have a large component in the positive x direction, 387 miles per hour, and it's going to have a much smaller component in the positive y direction, 50 miles per hour. And the total vector will look like that. So this is the velocity of the plane with respect to the Earth. So if I want to find its magnitude, I can use the Pythagorean theorem. So the magnitude of the velocity of the plane with respect to the Earth is going to be the square root of 387 miles per hour squared plus 50 miles per hour squared. So that gives me a magnitude of 390 miles per hour. Then if I want to find the angle, that would be this angle here, I know that the tangent of that angle, tan theta, would be opposite 50 miles per hour over adjacent 387 miles per hour. So to find theta, I would take the inverse tan of 50 divided by 387. And if I do that, I get an angle of about 7.36 degrees. And this angle is the angle that is north of east. So this would be 7.36 degrees north of east for the direction of my velocity of the plane with respect to the Earth. So that would be the new velocity of the aircraft. So here's a last question for you. Let's say there's a river that's flowing at 6 miles per hour. A person is swimming directly upstream at 3 miles per hour. So after 2 hours, where will the person be?